Okay, let me start. Welcome everyone to the lecture in GR. It's now already November and we have spent quite some time introducing mathematical concepts, and as announced, I will now fill these mathematical abstractions with life, with physical life. And I would like to directly start with something that one may either call a postulate or a definition. And maybe I'll just write both titles, definition and postulate, and then explain in what sense we can see it as the two of them. So the definition or postulate that I would like to state is about particles which we may interpret as test particles. So maybe you know from electrodynamics that a test particle is a particle whose charge is so small that we don't consider the influence of that charge to the surrounding electromagnetic field. And in the same way, we are now considering test masses, which should be sufficiently small so that their influence on the gravitational field, which in our case is, of course, the geometry of space-time, is negligible. So this particle just moves in a given geometry, but doesn't influence the geometry. And I will just in the future always talk about the particle without always mentioning that it's a test particle. And think of that as just sufficiently small. It doesn't have to be kind of really a point particle, because when I say the other effects can be neglected, it just means that we don't care about a certain going beyond a certain precision. And what small size really means in practice, of course, depends also, and we will see that, on the curvature of space. But small in GR is usually even satisfied by objects like entire planets. So when we, for example, study Mercury as a planet close to the sun, then the extension of Mercury as a planet will not be relevant to us. But of course, we should keep in mind that all these are approximations. And we anyway know from quantum mechanics that well-localized particles don't even exist. Okay, so the postulate is the following. World lines, or the world line of, okay, let me say in plural, world lines of freely falling particles of a given mass, and let me just call the mass m as an abbreviation, are time-like, and we have defined that last time. And that only applies if the mass is actually strictly positive, or light-like. That's the case if the mass is equal to 0 of the particles that we consider straight curves. Okay, so I mentioned that, I think, already last time. And remember, time-like just means, roughly speaking, that the velocity vector of the curve always has a length measured in terms of the metric g that we introduced that is strictly positive, according to our convention, plus, minus, minus, minus. And the light-like one is one where this vector has always length 0, which doesn't mean the vector is 0, because we have this Lorentzian metric. Now, why did I say it could either be a definition of a postulate? It really depends on what else we assume. And I think the cleaner view is the one where we see that really just as a definition. I still wrote postulate because that's kind of a common viewpoint, but it's a definition in the following sense. Remember when we introduced space-time, we said we first have a manifold, and then we equipped this manifold with certain structure. And we said in particular that one of the structures that we introduce to the manifold is the affine connection that defines parallel transport. And remember, the affine connection also defines what straight means. Without an affine connection, there is no notion of a straight line. So we had to ask the question, where does this connection come from? And the answer that I gave at that time was to say we can do an experiment. We often had experiments with gyroscopes, but in this particular case, it would be an experiment where we take a gyroscope in a certain direction and walk in that direction and always keep walking in the direction of the gyroscope. And that defines a straight line. Now, if I use that experiment in the other direction, I don't say I want to already have a structure on the manifold, I let it define by experiments. Then I would say by definition, what, for example, a particle does that freely falls should be such a straight line. So I do this experiment now, in this case, not with a gyroscope, but I just take a particle and let this particle freely fall. By the way, freely fall just means I have no forces. And as I said, gravity is not a force in this consideration, but I have no forces acting on this particle. So I do this experiment, I take particles and just let them freely fall. And then by definition, I say that whatever world line that defines, that must be a straight line. So in other words, the physics that governs the movement, the evolution of the trajectory of freely falling particles defines what a straight line is. And in that sense, I think it's reasonable to see that as a definition. Nevertheless, if you want to see it as a postulate, you should think in a different way. You should say there is already a notion of straightness somehow, which you have defined maybe independently, maybe you have defined it with some other experiments, or just by looking at the geometry of space-time, whatever that means. And then you say, now we introduce these particles into space-time and say, if they're freely falling, we observe they always follow straight lines. And in that case, it's a physical observation that you may postulate as part of the theory. Now, the reason why the definition aspect is actually, at least in my opinion, the preferred one is the following. If you only had the geometry of space-time but no particles, there would be simply no experiment to map out that geometry. So if someone comes and says, here is this space-time, and this space-time has a notion of affine connection which defines a straight line, then you ask this person, yeah, but what does that actually mean physically? Then he has to say something about a line is straight means that and that in physics. But if there's no particle, if it's just the geometry of space-time, there's no experiments he could do. So one necessarily needs the matter, the particles, to map out the geometry of space-time. And in that sense, I think it's reasonable to say that only with the particles, the geometry becomes a physical meaning, and therefore we use that as a definition of straightness. Okay, I now insisted a bit on this point, but I think it's really the basic of the whole theory. That's why it's probably worth thinking about that a bit more deeply. Now, maybe just a note that is actually quite relevant, although also quite obvious once you picture all these things. The parametrization of the world line. So what does the parametrization mean? So if I have a world line, I have, of course, a function from R to n. And this function has I usually use a parameter like lambda, and to each lambda, I assign a point in the manifold. So that's how I define a curve, gamma of lambda. And now I say that the parametrization of the world line is not physically relevant. When, at least in the case when you just only consider test particles. If you consider clocks, you may give it a meaning, and we will do that later. But a priori, if you just look at trajectories, there is no physical content in the parametrization. So what do I mean by that? Why is this the case? So when we talk about a world line, what we really mean is, of course, as a picture, something like that, we have the manifold, which is indicated in black, and then we have a curve on the manifold gamma, a worldline. Now the manifold is already an object in space-time. So in some way you could imagine that some of these lines, maybe the ones that going in this direction, mean that time, maybe according to a certain coordinate system, time grows, and there could also be another coordinate, maybe this direction here, that is one of the space dimensions. Of course, there are 4 space dimensions. I drew only one as usual. And now the property of the particle, for example, how fast it moves, does not depend on how fast you move here through the curve. That's the important point. That's really irrelevant. That has nothing to do with the velocity of the particle. The velocity of the particle is rather by how much the x, the position, somehow changes depending on the time coordinate. So it's rather the relation between this vector and somehow this vector. So in other words, if you here would draw a velocity vector like this, then the component in the t direction tells you how much time passed, and the component in the x direction how much you moved in space. And the relation between two, the quotient, has a physical meaning. And this quotient is independent of how fast you move through this curve. We will also see that actually more formally in a few minutes, but that's just to make you aware of the fact that we can arbitrarily reparameterize the curve and it doesn't change the meaning because we are already in space-time. This is of course not true when in classical mechanics you only consider space, because there the parameter that you're using is usually time. But the difference here in the 4-dimensional picture is that time is not the parameter. The parameter is just an additional mathematical parameter you introduce just for convenience to describe the curve. So in other words, you could say, in principle, you should be happy already if I just give you the set of these points without an actual parametrization. That would just be somewhat less convenient maybe to work with, but it would contain the same information, maybe up to a direction that is maybe stated.
Sorry to interrupt. Can I ask you a question?
Pardon? Okay, I didn't hear the question. Can you repeat it?
I said, sorry to interrupt. Can I ask you a question?
Yes, sure, yes, of course.
Now you introduced 2 velocities. I didn't get the other one.
Yes. Actually, maybe we will clarify this terminology. I was indeed now talking about the direction vector of the curve, which is that. And in a minute, or in a few minutes, we will call that the 4 velocity. So that's essentially the direction in space-time. Now, okay, thanks a lot for this question, because I should have pointed this out, that there may be this clash of terminology. So the direction of the curve in space-time, that's kind of a 4-dimensional object, if you like, because it's really pointing into a direction in space-time. Now, the velocity we are used to from daily life, speaking about velocity, if I talk about the velocity by which I run or so, then I usually have a 3-vector in mind, a vector only in space. And so let's suppose I just talk about the speed. The speed is somehow how much I change my location given a certain time. And so my point was essentially the speed in that sense, which corresponds to, let's say, the length of the 3 velocity is given by the quotient of the direction vector of the curve in this direction versus this direction. But maybe if it wasn't yet clear, please maybe wait just for 15 minutes or so, and then I will write down more explicit expressions about that, and then we may maybe come back to that discussion, if that's okay for you.
So the relation between the components of space and time will give us the speed that we're used to.
Yes.
And but this 4-vector direction of this gamma curve is something else, which you call it velocity for velocity.
Yes, that's kind of the 4 velocity. That's another object, right? Yeah, so essentially later in the terminology we'll introduce, this is the difference between the 4 velocity and the 3 velocity. At this point, what is relevant, or what I would want to say is not physically relevant, is is the parametrization. And I kind of illustrated this with this concept of velocity, but we will come back to that. But what you said is absolutely correct.
Okay, thank you.
Thanks for asking. Are there other questions? Okay, if this is not the case, let me now come with another, or introduce or state another, again, definition / postulate. And this is a postulate about the notion of time, or more precisely now, about how we measure time, namely clocks. So now a physical postulate, by the way, is not like a mathematical axiom. So I cannot formally phrase it. I will talk about things that we understand what they are, but that are not themselves modeled by the theory. Essentially, the very purpose of the postulate is somehow to relate a concept we know of in physics, like a clock, to a mathematical object. And so it's really the interface of the theory somehow to the real world that is made by these postulates. And that's why you should not try to understand them as very precise mathematical statements. And actually, as I alluded to many times, they are probably not, because again, when I talk about time shown by a clock, which I'm doing now, so the time tau shown by a clock, then you could ask, what's that really? And again, quantum mechanically, you would actually find out there is never an absolutely precise time shown by a clock. There's always some uncertainty. So this thing doesn't even exist. So it's again an approximation of a concept, but it makes a lot of sense as an approximation because, of course, in physics, we're all the time talking about time, and we know how to measure it with atomic clocks to a very high precision and so on. So this postulate makes, in that sense, a connection to experiments, which is in so particular also a particle. So a clock is in the sense of a particle as we used it in the first postulate, also a particle with positive mass. So whenever we have a clock, we assume that this clock is actually a massive object, which means it can only have a worldline which is time-like and not time-like. So there's no clock that moves at the speed of light. So now what do I want to say about the time? So the time shown by a clock. So think of a clock that is moving in space-time. So it has a world line. And now I say at any point of this world line. So for example, one point of the world line is the point gamma at lambda 2. So if I briefly go back to my diagram, there's a parametrization. And I could say maybe for parameter value gamma 1, we get this point. So maybe more precisely, I should not write gamma 1, lambda 1 here, but gamma of lambda 1. And maybe there's another point here, gamma of lambda 2. So these are 2 points. And at each of these points, the clock shows a time. So by a clock, I mean something which, wherever I am in the curve, for example, here, there's something shown by a clock. And this I call tau. That's, of course, the time. And now the statement is about the difference between times shown by this very same clock at 2 different points of this world line. So it's really just the time difference we would measure if we would move along this world line. So it's a very simple thing. It's just if you think of a stopwatch, you start when you pass here your stopwatch, and you press the stop button when you pass here in space-time, and then this time difference is what your stopwatch shows. And now the postulate says this object that you can measure, so this quantity that is physically defined, has now a mathematical correspondence in the theory, namely the length of the curve segment. So the curve may be longer than that. And what I mean by this terminal or this notation here is I restrict the curve to the parameter values from lambda 1 to lambda 2. So that would just be that curve segment from here to here. And of course, for a curve segment, we have a well-defined length. And remember, it's now important that the length is defined independently of the parametrization. So what I said before is still true. We don't need the parametrization to define the time that passes as a clock moves along this trajectory. So these are all things you probably have already heard, but I just wanted to introduce these things properly, because a lot of what we are going to do will depend on this understanding. So these definitions or postulates, I mean, for the same reason as before, you can see it as a definition. You can say it as a definition of length, because who tells you what the length is of such a curve in real space-time? There's nothing there that tells you that. The only thing you can do to measure a length is indeed to take a clock and move from here to here and measure the time. And that, by definition, is the length. So again, you should think of the metric, which underlies, of course, this definition of length as an object that is defined by a physical experiment. And in this sense, it's really a definition rather a postulate. However, again, if you somehow think the geometry of space-time would magically already be given, and now you're making statements about things moving in this space-time like clocks, then you may regard it as a postulate. But that's, again, in my opinion, a less natural view of the whole thing, because the space-time is just not given magically independently of clocks. You need the clocks to define the metric. Okay, so now you really establish the connection very precisely between the physics, real physics, things you measure, and the mathematics. And from now on, we will just work with these postulates. Now there's a convention that is, a convention is something that is often useful, but not necessary. There's no physical reason to introduce it. So the convention is that if we have massive particles, we often, and not always, we will just see examples where it's convenient not to do it. So maybe I should, add here something like often. So it's just something we may do. So we may choose the curve such that, so the curve, I mean now really the curve function, including the parametrization, in such a way that the direction vector of the curve always has length 1 at any point of the curve. That's also something you have already seen, probably in special relativity and already in that course. So why is this a useful convention? If we do that, then it's very easy to determine the length of the curve. Because if I now want to determine the length of a curve in the interval between lambda 1 and lambda 2 as before, then of course, by definition, remember what the definition is of a length. By definition, I have to integrate exactly this g function, the metric of the curve with the direction vector inserted. But this is now by convention 1, which makes this integral extremely easy. So the integral now just has the value lambda 2 minus lambda 1. So in particular, what this implies is, if you look at the postulate says that the difference of tau is given by the length. This means, of course, that the difference of tau is given by the difference of the lambdas, which I could also write as a differential, namely saying that if I take the differential of tau of lambda, so tau of lambda means tau at the position of the curve at lambda, maybe I should write this more properly, tau of gamma at lambda, then this is 1. So that's what we achieve with this convention. And then, of course, we can just use tau as a curve parameter, because now up to an additive constant, which just defines the offset where I start to run my clock, lambda and tau are now the same. So I just write this as a remark. We use tau as curve parameter. So we use now really the tau is now the time shown by the clock. So if you have a clock moving, we just will in the future assume that the curve parameter is the time shown by that clock. Okay, Are there questions up to that point? So as I said, these are all things that for those who already are familiar with special relativity should sound extremely familiar. But now what I want to do a bit later in this course today is to tell you in what sense special relativity is really a special case of the more general treatment. So which things that you have already learned in special relativity are actually still valid in these more general considerations. And if you don't know special relativity, you may just see that as a definition of what special relativity is. It's namely just a special case, of course, of general relativity for if we make certain additional assumptions. But to do that, I need some more definitions or terminology. And in the following, we will also talk about observers. Now, an observer, I don't think there's a common definition of what an observer is in physics in general. Actually, I've even attended research conferences where the title was about the notion of an observer in physics. And there are, people can discuss for weeks or years even what an observer is. And I think this is very relevant because for one thing, the observer that for what we consider an observer in general relativity is actually quite different from what we consider an observer in quantum mechanics. So if you want to bring together general relativity and quantum mechanics, we also need, probably even necessarily, to understand what is the common feature of these observers. And as I said, that's a current research topic, essentially. Now, having said this, I will here take a very simplified viewpoint, which, however, works for our purposes, and just say that we only look at one particular aspect of an observer. So in a way, you should not see that as a definition of an observer. That's by no means what I intend to do. I just want to say that if I have an observer, whatever that is, the observer will, in the context of GR, still have a world line. So an observer is defined by, in GR, by a world line. And again, I mean, you see already from that thing that this cannot be true in quantum mechanics, because in quantum mechanics, if an observer was a massive object, he could still, according to the uncertainty relation, for example, go through two doors at the same time in a superposition, and then he wouldn't have a world line. But that's just a remark to make you aware of the difficulty of unifying these concepts. So it's defined by world line gamma of a massive particle. So again, an observer cannot move at the speed of light. Together with a family of, and here I actually really don't know the English word of it. I call it a vierbein, and I think there is really no English word to that. A family of vierbeins. So vierbein is just, these are four vectors. So four vectors, E0, E1, E2, E3. So it's a family because I define them at any point of the world line of gamma. And now I have some conditions on them, so they cannot be arbitrary. One condition is that they should really kind of form a nice coordinate system in some way. So in the following sense, namely that if I look at the metric, I evaluate the metric. So E, I didn't write this, but E tau just means now the vector EI that is defined at the point gamma tau of the curve. That should be obvious that I mean that. It's just a simplified way of, I mean, I wrote in words that it's defined at any point. So it really means it's defined depending on the parameter of the curve, which I now take to be this tau for the reasons explained before. And now I say this should be eta. So eta is this symbol that is 1 if I and j 0 and -1 if I is equal to j and between 1 and 3 and 0 otherwise. So that's one condition. And the other condition is that the E0 vector should always point in the direction of the curve in space-time. So the direction of the curve in space-time, you should really think of, I mean, if you look here on the diagram on the right, if you have an observer moving along this world line, so if that's the world line of an observer, if the observer is at a certain point and moves here for the observer, of course, the observer doesn't move with respect to himself. So the observer would always kind of take himself as the reference of being at rest. I mean, let's consider that. And then the direction of the curve is then always a direction which points only in the time direction. There's no spatial component at any point. So that's what this thing here is saying. So the E0 vector is essentially the pure time direction of the observer.
Excuse me. I think there is a question. I think that Martin is raising his hand.
Yes, is there some precondition about how the EY and EJ change over tau? Because I mean, I could just take them arbitrary at every point, but I might also impose like a smoothness condition that they change smoothly along the trajectory.
That's absolutely correct. That was my next remark, which I don't, or let me write it. So everything, and I mean, that's a really important point, because otherwise it wouldn't make sense. But everything is assumed to be differentiable. Or you could even assume that it's smooth. So yes, it's a very valid question. We have to say that because we will actually take derivatives of these objects with respect to tau. And this is, by the way, true for all the objects I defined so far. So all these curves, the world lines, we will assume to be differentiable or even smooth. Now, this is just a mathematical convenience. This is not, I don't see that as a physical statement, because, as I said, it's anyway only an approximation. If we zoom in and look, is it really smooth? Is there really no kink in these curves? Then at some point we end up with a quantum description where it's actually just following the uncertainty principle and no longer well-defined. But for our mathematical treatment, we will exactly make this assumption. So yes, thanks for the question. Now, again, the way you should think of this, I mean, I had this diagram already before, but if this is the curve gamma, then the E0 vector is the tangent vector, and then the others are kind of spatial vectors, if you like. Because remember that the metric, I mean, this has to be the case already because of this. See, if we say that, for example, E1, if I and j is 1, this has to be -1, but -1 means it's a space-like vector. So except for the vector E0, which is just the time direction, as I said, time direction for that observer, all the others are spatial vectors. So you should think of E1, E2, E3 as a Dreibein, if you like this terminology, which defines somehow a coordinate system, at least a local coordinate system that moves along with the observer. And now you could have different observers that have the same world line, but their coordinate system is different. For example, one could rotate with respect to the other. So you could imagine that this E1, E2 of one observer, just in one chart, always E1 points to the right, as it does here, and maybe in another, or for another observer, we have the same world line, but the E1 in this chart seems to rotate around the curve gamma. Okay. So let me now come back to this question about velocities. And I hope this will actually clarify a few things that may have been unclear in actually all the treatment, because so far I think I made often examples where I somehow referred to velocities. And it may be worth if you go back to them once you now understand the distinctions between the different notions of velocity. So it's about the 3 and 4 velocity that I mentioned already before. And so let me just, yeah, these are concepts that I don't want to define formally. They are actually also not of so much importance for treatments purely within GR. They're more important to understand how does a statement in GR connect to our thinking that we are used to in, let's say, in a non-GR context. So they're not necessary. So the 3 velocity in particular is not a concept you need if you would immediately start thinking from your childhood on in terms of space-time as a 4-dimensional object. Okay, but let's first of all say that, or let me emphasize that what I will now define as a 3 velocity will be an observer-dependent quantity. So we fix an observer. So for a fixed observer, we consider a chart. Maybe, okay, I actually will need another symbol for the world line of the observer. So let me also mention that. An observer with world line. I call this world line this time delta. And the reason I call it not gamma is because we will have another particle that we consider, which whose world line I will call gamma. So now we consider a chart. So a chart, I guess you know well what that is. It's essentially defining a coordinate system in a region of space-time. And the chart should be such that the point with parameter 0, which of course I could choose where that is. So I just consider one particular point of this world line, and I, without loss of generality, say that this is the parameter 0 point. This should also in this chart have 0, the value 0 for all chart coordinates, or for all coordinates xi. And let's furthermore assume that this chart is chosen in such a way that the basis vector of the chart at this point, so this is the chart-induced basis, coincide with the sphere bind that is defined by the observer. So it's a chart that is very natural for that observer, because this, if you really think of this of the E vectors that I mentioned here as some physical thing that the observer carries along. So at least, I mean, the E0 is maybe not, I mean, this is just essentially, you don't need it. That would be the direction in which he moves in space-time. So that's for him always just a purely time-directed thing. So it's not clear what this would mean physically. But the E1, 2, and 3, as I said, are space-like things. So think of the observer carrying along 3 sticks somehow. And these 3 sticks are labeled E1, E2, as E3. And now we consider a coordinate system in which these sticks just define the coordinate directions at a certain point. Maybe not at any point, because things may change over space, over time, but at this point that we consider. Now, the note I made before, let me write this down here. I only made it in words or without writing. Note that the velocity vector, or okay, now I have too many velocities. Let me call that the direction vector in space-time. That's really just now, of course, as before, by definition, the d to the EPx0, because we said before that E0 is defined like that, and E0 via this condition is now the same as the coordinate direction. So this just means we have now a coordinate system according to which the observer herself moves into the x0 direction alone. So the x0 direction is in that sense the direction in which time increases if the observer is just at rest with respect to himself, if you want. It's okay, we'll see that in a minute, what that means in a diagram. So now we consider another world line. That was the reason why I called the world line of the observer delta. So let gamma be a world line, or the world line of a particle. And okay, here I think it could even be now a massless particle if you like, but I'm thinking for the intuition it's better to think of a massive particle, so it can have any velocity, such that at some point this particle actually crosses the world line of the observer. And let's assume it crosses it exactly at this point where the delta zero, for which we defined the coordinates and so on. So of course, if you have a given particle and you want to now look at that particle, you could go backwards and define the parameter of the observer such that it's zero when it crosses the world line of the particle. So the observer and the particle meet, and this is actually the only point where we can even define a velocity of the particle with respect to the observer. And that's, by the way, a difference to special relativity. In special relativity, you would just say, oh, there's this particle somewhere there, maybe on the moon, and I'm here, and there is a velocity of this particle with respect to me. Now, in general relativity, it's not clear what that would mean, because I'm here somehow moving in a certain direction, and the particle is somewhere else moving in a certain direction. And you know probably now very well that I cannot just take the vector of the particle without saying something else and move it to me and say, okay, now I can compare the vectors, because moving the vector of the particle on the moon towards me depends on the path I take as I take this vector back to me. You know, this parallel transport is path dependent. And so the velocity, the relative velocity of the particle with respect to me is of course only defined if I can somehow subtract the two vectors, the velocity vector of the particle and that from me, but I can only subtract them if they're in the same space. So I need to pull it back to my space, but that's not unique. So in other words, in a general context, there's just no unique way to define a relative velocity with respect to me. If space-time was flat, this works again, and that's somehow the special case of special relativity, because there moving back this vector towards me or pulling it back does not depend on the path. The parallel transport in flat space-time is path independent. Remember, that follows essentially from the geometric meaning of the curvature, which tells you if you go along a loop, how these things, how the directions change. And if the curvature is zero, they don't change. So I can take arbitrary paths. Now, let me finish that definition before, now come at least to the point where the three velocities defined. So now we have an observer and we have a gamma. And now I say, at least at the point where they meet, I can define a reasonable velocity. I call this the three velocity. So the three velocity, which I just call V with vector. So you could think of V with a vector arrow, but I prefer to underline these things. So the three velocity V relative, or okay, let me give the full thing, of the particle. Okay, maybe clear if I write it like that. The three velocity V of the particle that we just mentioned, relative to the observer, which we also introduced. It's actually a complicated object. It involves two different physical things. Is defined by V alpha, and alpha is now an index. And I usually write alpha Greek indices here if it goes only from 1 to 3 rather than from 0 to 3. So if I wrote something like gamma I or VI or so, then I usually mean all indices including 0. But here it's really only the spatial one, so it's a 3 vector. It's only 3 indices. And actually, it's not one of these covariant things. So let me actually put the index downstairs, because that's just the convention for normal vectors, 3 vectors. So they are now vectors that don't live in this 3-dimensional space. That's essentially really just a 3-tuple. It's not a vector in our sense of differential geometry. So maybe I simply shouldn't call it a vector, despite the fact that, of course, these are usually called vectors, but it's not a vector in our sense. It's just 3 numbers for alpha 1, 2, and 3, and the numbers are defined as gamma dot alpha. Here, the alpha has to be upstairs. That's the coordinate alpha of the curve divided by gamma dot 0 at tau. So what's gamma dot? So gamma dot I. So I is now an arbitrary index at tau. That's just to remember for you. We said that is essentially the i's component of the velocity of the direction vector of the curve gamma. Okay, so this now relates things I said at the beginning and also when answering the question that came up before. Let me make this diagram and then we can have a break. So if you look at this diagram here, I could of course write this in a chart. And the chart I take is the chart I now just introduced. It's a chart that is natural to the observer, which has a time mixed 0 direction and a spatial direction. And let's again just draw one spatial direction. So in some way, this will be the E0 vector in the tangent space. So the blue stuff is now the tangent space of that corresponding to that chart. That's these would be the vectors in this diagram. And now we have the particle moving. Now, of course, the particle moving has a chart representation, which is given by a tuple, gamma 0, gamma 1, gamma 2, gamma 3. That's really in this chart where the particle moves. And now what this definition is telling us, okay, if I scroll up a bit, is that the 3 velocity is just the fraction of how far per unit of time of the, if you want, of the clock of the particle. But of course, the parametrization is here not relevant, as I said before. But if I now look at the rate at which the spatial components change divided at the rate at which the 0 component, the time-like component changes. So in other words, if I write down the tangent vector here, so that's the vector whose components are given by gamma dot 0, gamma dot 1, gamma dot 2, and gamma dot 3. That's a vector in 4-dimensional space. And the claim is that these things are the rates of changes of the position, and this is the rate of change of time of this observer. And so, of course, velocity should be how much does the position change per time. So this fraction really makes sense in our normal understanding of what the velocity should be as a 3 velocity, as a velocity in space. Okay, now I just introduced the 3 velocity, and I will have to again say what is now then the 4 velocity. But actually, maybe the short answer is the 4 velocity is just actually this the vector v itself. More precisely, of course, I could express it in coordinates. So these would be the coordinates of the 4 velocity. So the 4 velocity exists without the observer already. The 4 velocity is really just the vector pointing in the direction of the curve. And of course, this curve has a direction vector independently of an observer. Of course, if I want to write it in components, then I need a coordinate system and so on. But I made this point very strongly when we introduced differential geometry, that a vector doesn't depend on coordinates. A vector is really just the direction of the curve. Its very definition says that. And so a particle has a world line, even if there are no observers around. So therefore, it has a direction vector, and that's this 4 velocity. So the 4 velocity is not, in that sense, a relative velocity. It's a property of the trajectory of the particle by itself. Whereas the 3 velocity is a highly observer-dependent thing. It tells you in the coordinate system defined by the observer, how do the spatial coordinates change in relation to the time change. Okay, please think about that. It's all very simple formally, but I think it's nevertheless good to think about a few examples of how does this now work for in this particular case where you have, for example, let's say the twin paradox. And maybe I'll go into that just as an illustration. But let's first make a break until, let's say, 10 minutes should suffice. So let's say until 5:02, and then we convene. And of course, as usual, I stay here for questions, in particular as I didn't have time to take questions for during the last 2 lectures, or at least not after the last 2 lectures. Are there any questions?
And excuse me, I have a question. It's about this sphere bind that you introduced, this E0, E1, E2, E3. They are the basic element, also the basis of a vector, for the space-time. Am I right? They are the basic. They are the basis.
Yes, you can. Yes, right. So they form certainly a basis at that point of the tangent space, not of space-time. So, but that's what we ought to mean. I mean, space-time is the manifold. The manifold itself doesn't have a basis because it's not a vector space. But normally what they are vectors in the tangent space at any point along the world line of the observer. So the observer, and of course, if you can think of, okay, maybe add that to the diagram. So I could have an observer in green here. So an observer like moves like this, for example. Now the observer meets this world line of the particle that he wants to observe, and at any point, so this would be the delta thing, at any point along this green world line, there is a coordinate system, and hence in particular at that point where it meets the particle. So here there is a vector E1. So this vector is now, okay, I draw it in the same diagram, but it's really kind of a vector of the tangent space. So maybe a better illustration would be to indicate with yet another color, let's say blue, that there's a tangent space, P, PM, or delta 0 is the point, M, and then the vectors live in this blue space. So there's, for example, a vector E1, and there's also an E0, which is the tangent vector, and there would also be E2 and E3, which I don't draw here. And so you see, at this point, there's now a well-defined basis of the tangent space. And because the velocity vector of the orange curve of the particle world line is, of course, also an element of the tangent space. It's a vector in this direction here. I can now talk about this vector in terms of these basis elements.
And so you write the indices down because they are basic elements.
Yes, right. Yes.
Okay. So, but if in a general vector, in a vector space, in our tangent space, the indices are usually up.
Oh yes, that's okay. That's a very important thing to be aware of. So thanks for bringing this up. So there is a big difference between saying, okay, maybe I'll write this here separately on a page. So if I have vectors like E1, E2, E3, or okay, in this case it would have been E0, E1, E2, E3, each of them are then elements of a tangent space. So each of these things is an element of TPM. And the index is somehow talking about which vector I mean. So there are 4 different vectors. Now, if I have one vector, so let me now take one, or let's say another vector, not necessarily the one of those. So I could now take a vector X element of TPM. Let me call it V. I think I often call vectors V. Now, I could ask what is a component of this vector. So V0 is now a real number. This is not, you see, it's a different thing. So here E0 means it's the whole vector that has, because I have 4 different vectors, I need an index to indicate the different vectors. Whereas here I have one vector given, and now I'm referring to the coordinate of this vector with respect to some coordinate system. So if I now want this to be well defined, I need to say with respect to which coordinates. I mean, these are just defined per se. I just give you a list of 4 vectors and label them with little label sticks. And say, look, this stick is the vector E0, this stick is the vector E1. Whereas this thing is defined once you have a coordinate system. So I could now say, let's take this thing here as the coordinate system. And then you remember that we have the dual coordinate, the dual basis, which is called like this, epsilon 0 to epsilon 3. And now V0, the component of the vector with respect to this basis here, is defined as epsilon 0 applied to the vector. Maybe I could also express this without the dual basis. So what I mean by this, or another way to say that, is that V, the vector, is actually the component, which is a real number. This is a real number, times EI. This is a vector. So here you see again, these are different objects. This is a vector, and this is the coefficient, which is a real number. And here you also now see why it has to be like that, that the index here is downstairs and here upstairs, because here I apply the summation convention. And okay, I mean, this is not a reason why it has to be that, but it's at least consistent. Here we can apply the summation convention. And we said whenever we can apply the summation convention, then we have automatically guaranteed that things transform in the right way. And so if the thing on the left-hand side is basis independent, if I would now change it to another basis, E prime or so, then this thing would transform and this thing would transform, but they would transform in different ways, exactly in somehow dual ways, such that the transformations cancel and the whole object is again the same, which it has to be because the left-hand side is independent of the basis. So the summary of your answer is these indices really label the different vectors, whereas if we have a given vector and I write an index like Vi, then I mean the component of a vector with respect to the basis.
Okay, so in special relativity, we define the contra variant position full vector. These are the odd indices 0, 1, 2, 3 up. So they're here actually the coefficients for the vectors.
Yes, so
okay,
like the 4 vector in our case now, or maybe we have here, yes. So this would be now the 4 vector that you see here. So this gamma dot, because these are the coefficients. Okay, maybe I wrote it. Yes, you see here the gamma dot I. This is the dual basis element. This would be what I here down called the epsilon 0. So that's exactly this. So it takes out the i's component of that vector. So this is in some way it's usually, I mean, this is just called the direction. But the components of that vector, of that direction vector, so this is only one vector. So this thing has no index at all. It's really just this arrow. It's the arrow, if you like, or the direction of the curve of the particle you're interested in. And now you want to talk about the components of that vector. And there are, of course, 4 components in space-time. And these 4 components, this 4 tuple, is usually called the 4 vector, also in special relativity. So indeed, as you correctly said, if you see in special relativity 4 numbers with these indices, these are exactly the 4 numbers here for I equals 0, 1, 2, and 3. So that's the 4 vectors.
Oh, okay. I have another question also about this observer. You said that it's a family of this sphere-bind. This family is with respect to tau.
Yes.
Like
yes. I forgot to put that.
Okay.
Yes. The family is with respect to tau. So for each tau, I have such a sphere-bind.
Okay, good. Okay. Thank you. That will be all.
Okay, you're welcome. Thanks for questions. Are there other questions?
Yeah, there was one question in the chat. I think I think I already answered, but I'm not sure about the answer. And they are asking whether the last diagram you draw with the x0, x1 with the curve, whether this is just somehow the generalization of a Minkowski diagram for spatial relativity, but I think it actually is a Minkowski diagram.
Yes, I will actually just come to that connection to Minkowski diagrams. So that will be the topic of the next hour.
All right.
Okay, I think it's time to restart. Of course, I keep taking questions if there are any. But before I actually start, I have two small admin things that I want to sort out. Okay, the first is just more or less an announcement. And there will be an evaluation of the course. Now, because this is kind of a joint course between the university and ETH Zurich, there will be two separate evaluations, one carried out by the University of Zurich and one by ETH Zurich. Now, of course, only the University of Zurich students should take part in the university evaluation and only the ETH students in the ETH one. I don't think there will be evaluations by Basel, but this could also come. That'd be fine for me. Now, I was just informed that the evaluation form for the University of Zurich students is now online. The students who are in the course should have received an email with the access data. So I would just like to encourage you to use this opportunity and give feedback on the course. Of course, you may also just give me feedback directly if you prefer to do that, but of course, I'm happy about any type of feedback. So if you do that by this evaluation, that's most welcome. I was also asked to give you 5 minutes of time during the lecture to do that, but now because we have other students who can now not fill in the evaluation, I hope you understand that, yeah, I will, it's better not to do that now, but I hope you find some time right after the lecture maybe to do this or during the lecture. The other thing are the exercise and Q&A sessions. So we have set up a Q&A session. I mentioned that I think a few weeks ago, where you can post questions to the course or to the exercises on Moodle, and then the teaching assistants, in particular Dixina and Eleanor, would then discuss and answer these questions in a special session. Now it turns out that so far there was very little demand for such a session, so there were only, or I think even none this week, questions posted. And I just wanted to ask you now, those who are present, whether you think it's still useful in the future to have that or not. So let's make a small poll. Who thinks that it would be good to keep that instrument where you could submit questions? If you say yes, then of course, I would also encourage you to actually use it, because it's a bit discouraging for the TAs if they are there for the Q&A session and no one appears. So yes, please vote now, yes or no. So no would mean you don't really want that instrument, and yes would mean yes, it could be useful in the future, and then you should really feel encouraged to use it. Okay. Yes, okay, so there were 10 votes yes, 10 no, and I'm not sure what the other 60 people think, but okay. Thanks a lot for this feedback. Then another question is about the exercise classes. That's my last question. There is one offered also by Eleanor and Dixina on Friday morning, which is the time that was not originally on our schedule. And I think we thought it may be useful for some students. Now, if someone wants to attend that one, so please first reset your vote. You have already casted for the previous question. And then, maybe I do that briefly. So now if you want to vote for, if you're interested to have an exercise class on Friday morning, then please vote yes now. Okay, I think
they are asking what the poll is about. I think this is for the exercise session on the morning.
Exercise session. Yes, maybe I wasn't clear. So at the moment we have an exercise session. Let me just check the time. Yes, so the exercise session we have at the moment is off by Eleanor and Dixina on each Friday at 11. And the question is there an interest to attend that? Because it's a new time. And, okay, I see there are 5 or 6 people who are interested. Okay, thanks a lot for that feedback. Okay, then let me continue. We have now introduced this concept of a 3 velocity as an observer-dependent quantity, and that's really the 3 velocity that you would assign to normally in our usual understanding of velocities, in our classical understanding of velocities, to an object that is moving. But let's try to understand this a little bit better. So when you look at this definition, I just put this quotient here. So what does this actually mean? So it means that, okay, let me first just write it in different terms, because there were some questions in the break, and maybe it's useful if you see it in the following way. So the 3 velocity obviously has 3 different components, V1, V2, V3, and what I was saying could just equivalently be expressed as follows. I mean, this is kind of a conventional vector notation, that I take the 3 components of the gamma dot. So gamma dot are the components of the direction vector of the world line. And I rescale them by 1 over gamma dot 0. So that's this quotient. So there's nothing new in this format. This is just a different way of writing it. Let's now analyze this a bit, and for simplicity, it's kind of useful to just assume that, actually it's without loss of generality, to assume that the velocity is such that it only has a 1 component, and the 2 and 3 components are 0. Of course, I can always choose the coordinate system or these vectors E1, E2, E3 in such a way that E1 points to the velocity of a particular particle I'm interested in. And then, if you look at this formula, it means that the absolute value of this vector V. So this is now the normal Euclidean norm of the vector. So of V. So V is a 3 vector, so it's not a vector in this differential sense. And so we just take the Euclidean norm of that is now just gamma dot 1 over gamma dot 0 in this special case. That's really the relation between these 2 things. So that's all almost trivial, but let's now see how this relates to other things. So let's now assume that we are indeed in a convenient coordinate system, and I told you before that a convenient curve parametrization, and one that is convenient, that was wrong. The convenient one is one in which the velocity vector has length 1. That's what we said before, it should be a convention. And I'll just remind you of this convention. And of course, if we made this convention, then in this particular case where there's only a 0 and a 1 component, we have this relation. Because remember that the coordinate system, the E1, E2, E3, and E0 were chosen in such a way that the G between them is equal to eta. So that's this condition here, which means if I now evaluate the components of the vectors, I just have this type of metric where I multiply the 0 components with 1 and the spatial components with -1. There should be a square here. Okay, if you now look at this formula, so this is just the convention that we introduced, but this convention is useful. And by the way, in special relativity, that people talk about 4 vectors, they always make this convention. So this is only a convention that is in special relativity also quite usual. And now I just insert this convention in this formula here. So this allows me to write everything in terms of only gamma dot 1, because I can now express gamma dot 1 just as gamma dot 0 in terms of gamma dot 1 and plus squared plus 1 and the square root of this. It just follows from this. Okay, maybe it's convenient actually to rewrite this to see the symmetry. And if I rewrite this a bit, I square it on both sides, and yes, okay, this is all kind of trivial operations. I square it and multiply it with the 1 plus gamma dot 1 squared, then I get this expression here. And that's an equivalent. And now I can again solve it for gamma dot 1. This is now very simple algebra. I'm just doing it for a reason you will just see. So I can now solve this equation for gamma dot 1. And obviously, if I solve this, I can easily verify, I get this expression. And similar for gamma dot 0. Now I can just again use this relation here and write gamma dot 0 as 1 plus gamma dot 1. And if I do that, you see if I add here 1 to this, I'll just immediately get, okay, let me write it. I get 1 over 1 minus v squared. So what we have found is the following relation. We have seen that if I just write down the first components, gamma dot 0 and gamma dot 1, now I take again the square root on both sides. We have found this expression here, 1 and v. And okay, we were now in the special case where the velocity just goes along the one coordinate. Of course, we could also do it along another coordinate, or in the general case, maybe I'll now go back to the general case and just rewrite the same thing. So it's obvious that if this is in the special case where the velocity goes along the one component, then in the general case, I could write something of this form here. This is equal to 1 over square root of 1 minus the v vector squared. And then I have here a 1, and then the components of the v vector. Okay, that's what we found. And so now again, for the terminology, this thing here is the 4 vector. So is a 4 tuple of numbers corresponding to the components of the direction vector of the worldline of the particle in a given coordinate system, in this case, the coordinate system given by the observer, whereas this thing here, not the whole thing, but these 3 together, this is the 3 vector. Now, those who had, again, special relativity may have seen exactly this relation. And now you probably see why it's kind of often very cumbersome in special relativity to work with 3 vectors, because that's obviously a much more natural object. And that object is kind of directly defined in space-time. And you see this very natural object from a space-time perspective is now usually expressed in our, let's say, classical non-relativistic or pre-relativistic understanding by objects which have this additional scale factor which involves the square root. But of course, this square root causes a lot of trouble. I mean, that makes the whole thing highly nonlinear and so on. So it's not, I mean, the purpose of this short interlude with 3 vectors is not to encourage you to use 3 vectors. It's just to make the connection to what 3 vectors are. Because as I said before, the 3 vectors are really what we would measure if we measure how much does something change in space relative to how it changes in time. And that's a measurement we do with respect to us, with respect to an observer. So these are the things we measure. But then to work with the things, with the quantities. It's better to actually think of these objects as part of space-time.
I think there is a question from Martin.
I might have missed this, but if I see it correctly, in comparison to the formula I know from special relativity, we have set the speed of light to 1 here.
Yes, that's right. Yes, yes. Thanks for the remark, but that's correct. We had done that essentially. I mean, yeah, probably it's a long time ago that I somehow mentioned that we will in GR always work with C equal to 1. And actually, maybe a reason is that we don't want to be like British people. You know, the British kind of measure lengths depending on whether they measure horizontal lengths or vertical lengths in different units. And this is quite cumbersome. I was actually always struggling with that. So, for example, how tall I am is measured completely differently with different units than what's the distance between my office and my home, which is maybe in yards or miles. And yes, and anyway, it's a big mess. And somehow we are doing the same if we are using seconds and meters, because space-time is just, of course, a 4-dimensional thing. And now we somehow say, let's measure one dimension with a different unit than the other. That's obviously not a good idea. Of course, there's a good traditional reason why it was like that, but in retrospect, it's a very bad idea. So setting C equal to 1 just means that we are measuring everything with the same units. And that's the only natural thing to do when we're talking about space-time, in particular when we realize that this time direction is not well defined. This is observer dependent, which is, of course, by the way, also the case for vertical and horizontal, because you may also ask whether this is generally defined. Anyway, thanks for the question. And from now on, let's just again keep in mind that whenever a V appears, if you want to express it in your units, it's a V divided by C. It's the fraction it has compared to the velocity of light. So the thing you have probably seen here, the formula you're familiar with, is 1 minus V squared divided by C squared, because this whole thing has to be dimensionless. And the velocity in these natural units is, the 3 velocity is dimensionless because it's meter, it's length divided by time. And if both have the same units, the units cancel. Okay, now let me, I said that before, it's maybe good to think of examples, and actually let me do an example at this point. And it's the example you're probably very familiar with if you had special relativity, but don't, I mean, okay, maybe think, okay, I've seen that many times. I will nevertheless do it. And maybe one purpose of it is for you to understand what is really now different in the twin paradox if you look at it in special relativity or general relativity. So what's the twin paradox? Essentially, it's a story of 2 twins who are born somewhere. So that's an event that they were born. And let's suppose we are sufficiently coarse-grained that this is just one event where both were born. And now they move around in the world. And let's suppose they meet. I mean, they may even meet in between several times. But let's suppose they meet. Okay, let's not make the story complicated. Let's just assume they meet once again. Doesn't need to be realistic. Now, let's call one twin A for Alice and the other one B for Bob. That's, by the way, a convention that comes from quantum information theory or from information theory in general. And now we can ask the question, what do their clocks, or how old are they? Which is, of course, in terms of clocks, just what would their clocks show? What time would it show if they started their clock when they were born and would always take them with them during their lives and then compare them? Of course, the age is just a biological clock. So the question is, how old are they when they meet? Now, it's obvious, according to the postulates and so on that we introduced, that, first of all, they can, of course, have different ages because the time shown by the clock was a property of the worldline. And so clearly, if the worldline are different, this clock may show a different value. Now, the first point I would like to make, in particular to those who already have seen that in special relativity. In general relativity, there is not necessarily a notion of one of the two staying at the place where he is. So in special relativity, you often have this paradox: one of the twins stays on Earth and the other flies away with a spaceship for 10 years and then comes back. And then there's an a priori asymmetry that you say one really travels away. Now, if you have general space-time that may be curved, there is simply no way you can say one stays where he is. Both just have world lines. And the only way to determine what the clock is just to measure the two world lines, the lengths of these world lines. So the time difference is essentially given by the length of this curve minus the length of this curve. And that's something you can calculate. And this may be complicated depending on how the geometry of the space-time is given, but it's just that. And see now, if I look at the coordinate system, I may choose a coordinate system which is very natural for the twin A. He may say, I take a coordinate system in which I always stay. Let's suppose it's the guy who stays on Earth. He says, Earth is my reference point. So my own path is just moving upwards. Of course, he may move around a bit in the village where he lives or on Earth, but roughly speaking, he moves like that. Let's suppose there was really one flying away with a spaceship, B. And so in this coordinate system, it would look like this. So this is now one chart. So I think this whole example should illustrate the notion of choosing different charts. So that's x of gamma A, and that's x of gamma B. Now the other twin may also choose a coordinate system, and he would say, no, my spaceship, let's suppose B really goes on a spaceship, so my spaceship is just where I am, and that's the point from which I measure everything else. So I want to have a chart map Y in which I'm the reference point. And then he would say, in this chart that I chose now, the trajectory of my twin A looks a bit different. So that's now Y of gamma A, and the orange line is Y of gamma B. Okay, so far so good. This is just to illustrate that a priori in GR, both is equally valid. There's no preference given by GR for one of these two. Now, why is it that in special relativity we usually phrase the paradox as in an asymmetric way? And actually we want to, because one really will remain younger than the other. So let me first now make a claim, which is actually independent of the twin paradox. That's a more generally valid claim. I will not prove it. Maybe I plan to maybe add a proof sketch into the lecture notes, but the claim is the following. If space-time M is flat, so let M is the manifold describing space-time, and being flat means that the curvature tensor is 0. And I just write it now in components. This wouldn't have been necessary, but just to make clear, I'm really talking about this 1,3 tensor, the Riemann curvature. Then for any P, for any point in the manifold, there exists a chart Ux around P such that G, so G in this chart, so these are now the components of G, that's a chart-dependent notion, at the point Q is equal to eta ij for all points Q in U. Now, you may immediately think of the normal coordinates, and then you may even ask, well, didn't we already prove that even? We introduced normal coordinates, and we said there is always a chart such that the metric looks like this, such that the components of the metric are exactly given by this eta symbol. But now this is much, much stronger, because in the case of the normal coordinate system, I emphasize that this is only valid at one single point P. So for any point P, we can find a chart. But here I'm making it a different statement. I'm saying around any point P, there is a chart such that for all points that are still, of course, the points have to be in the chart domain, otherwise I cannot even talk about this, but for all points that are covered by the chart, and the chart U has to be an open set, so that's certainly not only one point. For all these points, it still has this form. So I can move a bit around the point P, and the metric always keeps this very nice form. And that's actually, we call these coordinates Minkowski coordinates. So, I mean, a chart defines a coordinate system, and this particular chart, if the chart has this property, which is only possible in general if the M is flat, otherwise I cannot even do it. But in flat spacetime, I find such a chart, and then I have these Minkowski coordinates. So it's somehow Minkowski, so one can certainly say Minkowski coordinates are such that they are normal coordinates for all points in the chart. So they're kind of more globally normal coordinates. By the way, just as a remark, this does not imply that the whole space is kind of cannot have an interesting topology. So you could have a flat space-time, which globally speaking is still a torus. So it could be that you walk in one direction for a long time, and then you just realize you're again at the same point, but everything was flat. So this actually happens if I take a piece of paper here and I just bend it like this. Then according to the Riemann curvature notion, this thing, and it looks curved, but it has no intrinsic curvature. So you know now what curvature means. It means that if you make a loop, take it parallelly transport the vector along the loop within that on the piece of paper. So think of a little bug that moves on this piece of paper. He would not see a deviation of the vectors or the path-dependent deviation of the vectors, because for the bug, all the parallel transport in this plane looks the same as if the paper was unfolded like this. So it's really just the same as a flat paper. And therefore, what this means is that we could in principle have a torus, and we could do that in all dimensions, and that could still be flat. So that's just to say that the condition that we have a flat space-time in that sense, in this local sense, that at any point the curvature tensor is 0, does not imply we have essentially just a normal Minkowski space that is infinitely extended. But what it means is that at least locally within a chart, a sufficiently small chart, we can do as if we were in Minkowski space. Now we can actually say once we have this, so once we go now to a flat space-time, we can introduce an asymmetry, because in flat space-time, it cannot be that both this chart and this chart are Minkowski charts. So in general, none will be, but if we now assume that one observer really rests, is never accelerated, and space-time is flat, then for that observer, it's true that if he draws the diagram, so let's suppose A was such an observer that doesn't accelerate during the whole experiment, during his whole life here, and space-time is flat, then this would be a Minkowski chart. Whereas this wouldn't, because here the observer actually is not a straight line. And of course, this means here that an unaccelerated observer is really looks straight in the chart. The lines, the chart representation of straight lines really look also straight or are also straight lines. Okay, so now once we realize that the difference, the asymmetry can only be defined if one of them has a special property, remains at rest, and therefore has a Minkowski chart, then we can really come back to the usual formulation of the twin paradox. And just then for those, this is now really for those who didn't have special relativity before. I want to still mention that. So in this case, one usually looks at the situation like this. So as before, there's now an inertial observer, so that the one that doesn't move, let's still call it gamma A, and the other one moves. And so a simple situation would be that it just moves straight away and comes back straight, and that's gamma B. Now let's suppose that we choose the units of time and space. That would be the same, but you can still choose them in such a way that here when they meet again is 1, and here is 1/2. So let's suppose 1 is a year or so. And now what we could do is to use for the curve gamma beta x0 as a curve parameter. So that's now not our general convention, but use x0 as parameter for gamma b. As I said before, everything physically is independent of that choice. That was just a convention to use tau, but we can use, if a problem demands so, or if it's more convenient, we can use a different convention, which we do here. And now, as I said, now the calculation is very easy. And I just want to illustrate here how we retrieve a result that those who did special relativity already know. But for those who didn't know it, you can now just see what you do. So that's special relativity is really the special case where we have everywhere Minkowski coordinates. So Minkowski coordinates not only in one chart, but essentially globally. That's what special relativity is. So it's more than just saying it's flat. It's really saying it's kind of flat and globally, admits globally Minkowski coordinates. And then, but this is just a convenience. So that's really what special relativity is about. Now in special relativity, in addition, one has the kind of general attitude to always work with Minkowski coordinates and never with other coordinates. But of course, I could also in special relativity work with other coordinates, and then I would still have all these gamma symbols and so on. So that's independent of, that's an independent choice. So I think the physical choice is really that we are in flat space-time, and then it's convenient in addition to work only with Minkowski coordinates. So in other words, it's a different thing to say the space admits such coordinates and that we have to always work in them. So now let's calculate the length. And this is now extremely trivial. So let's calculate the length of the world line of Alice. So what's that world line? I mean, the curve vector, the velocity vector of the curve is just, of course, the vector in this direction. So that's the d to the dx0 vector. That's this vector here. That's in which direction gamma A moves. So we just chose it in such a way that it doesn't have a spatial component. And so this integral, I mean, now for gamma A, we could even take the proper time if you like, or actually, we could also take x0 as a parameter. It doesn't matter. At the end here, we just get 1 because this thing is, of course, 1. By definition, because eta 0, 0 is 1. Now, the length of gamma B is, okay, here we have 2 curve segments. One goes from 0 to 1/2, and then we have the whole metric. Now we have to write the vector gamma. We have to write the velocity vector of gamma B. So what's the velocity vector of gamma B? Yeah, maybe I should, okay, to really see that, let me do it properly. And to do that, I would actually, it's useful to really write down the curve parametrization. So if I say I use x0 as a parameter, then of course the curve is given first of all by x0. That's just also the parameter. And then the spatial component is given. Now I use the v, the 3 vector v, or the 1 component of the 3 vector. So remember that v was defined as the quotient between this and that. So I can now just say if something moves with velocity v, then I just write the curve as this, and then I automatically guarantee that the 3 velocity is v. So we have now the situation where Bob, observer Bob, moves with 3 velocity v relative to the observer A in the one direction, so the other components should remain 0. And now it's easy to take the derivative, of course, because the velocity vector gamma dot is, of course, just the derivative of that. So gamma dot is gamma dot 0 is, of course, just 1, and gamma dot 1 is, of course, just v. And now you see what happens. I mean, let me maybe write this immediately in terms of components. So we have now g ij, but okay, I'll just write it out. So g00 times gamma dot 0 plus g11 gamma dot 1 gamma dot 1, and the other components are anyway 0. And now you see this g is, of course, 1 because it's eta. This is -1. So what we get, and then okay, we have the second curve segment. I will not write this out. This is just the same with the other direction. We just can at the end multiply everything by 2. So now I insert things. So you have this integral here from 0 to 1/2. So this is the curve parameter was dx0, and gamma dot 0 was 1. So we get 1 in the square root 1 plus or minus v squared. So maybe I'll put here also an absolute value around v as before. And then we have this expression here. And of course, if I integrate this twice, and we have twice the same thing from 0 to 1, then what we get is just exactly this factor. So we get square root of 1 minus v squared. So in other words, what we found is that while for Alice time 1 passes, 1 year, for Bob only 1 minus v squared square root passes. And this is the time dilation, you know. So this is now kind of the GR approach to the twin paradox. Of course, it's very similar to what we have seen in special relativity. It's just now you see that this outer viewpoint and not using v too early, just work with the general definitions, the general lengths of curves, and just v only appears here in how I see the curve leads us to this formula of the time dilation for the twin paradox. And of course, again, if you had c not equal to 1, this would be 1 minus v divided by c squared. Okay, are there any questions regarding that? So that was now the part where I made the relation to special relativity.
I have a question.
Yes, please.
I thought that so Alice would be on a geodesic, right? Since she's
yes, in this case she is. Yes, yes.
Isn't a geodesic supposed to have the minimal length of the curve?
Aha. Yes. So that's a good point. So thanks for raising that as well. So I maybe remember when I introduced geodesic, I was actually careful to say it's an extremal point. Now it turns out that in GR, it's in fact most of the time a maximal length. So it's really true that the way you can maximize the time between 2 points is actually by not moving. So it's really the other way around. So the statement is, if you don't move, so if you move along a geodesic in that sense, if you don't move, if you just stick with that straight line in space-time, then most of the time passes. And so the more nervous you are and move around, the less time passes. That's maybe a daily life experience, but it's also true in relativity. So, by the way, there will be an interesting thing about that. We will later, I think maybe next week, analyze how much time passes when you cross the horizon of a black hole until you hit the singularity. When you cross the horizon, nothing bad happens to you, but when you hit the singularity, you're probably dead. And now you can ask yourself, how can you maximize the time you still survive once you cross the horizon? And it turns out that probably the best strategy is just to not move, not try to move away from the singularity, because then by moving around, less time will pass for you and you will live shorter until you hit the singularity. But let's analyze that in more detail a bit later. But it's a general thing that we maximize. So geodesics and GR maximize the time. Now, okay, maybe I will immediately now make another remark about special relativity, which is the last remark about that. From then on, now we will leave the realm of special relativity. Of course, we will still sometimes look at non-curved space. Actually, we'll even do that after tomorrow. But let me, for the moment, explain what is the role of Lorenz transformations. Because if you had special relativity as a topic already studied, you may have encountered Lorenz transformations as the crucial ingredient. They appear very early in the theory, and everything is somehow built up in them. But now I haven't talked, I mean, when you look at this derivation, there was no Lorenz transformation whatsoever. There was just nothing of that type here. It just calculated the lengths of curves. And there was no coordinate transformation at all. We just looked at the coordinates of Alice, but not those of Bob, but we didn't Lorenz transform. So where do they appear? So actually they appear in the following scenario. Let u x and u x tilde be two different, or two, I mean, they don't necessarily need to be different, two normal coordinate systems or chart maps. So I will now write coordinate systems, but you can identify this term with the term chart map at a point P. So now we are again, I mean, I start with the general features. I'm not at the moment talking about flat space-time, but of course it will in particular be true for flat space-time, such that the following hold. So let's suppose there's a, okay, and this is actually not really a condition, but let's, okay, maybe I just end here. So let's just have these two normal coordinate systems. And now we define a transformation matrix gamma mi, lambda mi, sorry, lambda mi be defined by how the charts how the coordinates transform if I move from the tilde chart to the non-tilde chart. And you see, the U is the same, so I assume they have the same domain. You can, of course, always take the intersection of the two domains in general and just define that as the new domain, so that's no loss of generality. And of course, a chart transition map can always be linearized. So remember that the 0 point is by definition the same, because the 0 point is at the point P. So I have no zero order term, but I may have a first order term, and I may have second order terms, something like that, gamma I squared or something. Yeah. I mean, by this I mean all higher order terms. That's a general notation that includes also third order terms and so on. So if I have that, then obviously the transformation rule between the two, I mean, you should by now be very familiar with these transformation rules between coordinate charts. So if I take the metric and I just transform the metric according to the usual transformation rule, that's the usual rule, then if I now insert this, so this can be very easily evaluated. The derivative of xn to the x tilde I is just, again, this matrix, because in first order it's that, and I'm only interested at the point P. So let's only do that at the point P. I'm not writing this here, but just keep in mind, I'm only evaluating the thing at the point P. Then I have this thing here. That's the expression I get. But now, because they are normal, so since by the condition that these charts are normal, they're both given by this eta function. So the components of the chart are the eta functions. So in other words, the condition just reads that eta ij is equal to lambda mi, lambda nj, eta mn. And that's by definition, so by definition, lambda mi is now are the components of a Lorenz matrix, or I mean Lorenz. Let me just write more colloquially, more Lorenz transformation. Of course, I mean the matrix is defining the transformation. So if you look in a book, what does a Lorenz transformation? How is it defined? It's exactly defined by this relation. So the components of the lambda matrix satisfy this relation. So in other words, the Lorenz transformation appear as the lowest, these matrices appear at as the lowest, excuse me, lowest order terms of the transformation rule. Now, if I restrict to linear transformations a priori, if I just say, let's only look at linear transformations, then, of course, this whole thing disappears, and I can just say the transformation between coordinate systems are just given by Lorentz transformations. Now, what does this have to do with special relativity? So let's now take all assumptions that are usually made in special relativity, and then you see that the Lorentz transformations remain. So in special relativity, we usually take Minkowski coordinates. Now, as I said before, Minkowski coordinates are in particular normal coordinates, so everything that I said here applies. Furthermore, in special relativity, one usually only considers linear coordinate transformations. That's just the choice one makes. That has no physical reason. It's just that for some historical reason, maybe also for convenience, we just say in special relativity, we are only interested in coordinates that are linearly depending on each other, which actually has to do with this fact that we only look at inertial systems, because in an inertial system relative to another one is one whose coordinate transformation, if I define the origin of the system as the coordinate 0 point and so on, and transforms linearly. So if I make both restrictions, I go to flat space-time, and then I know they admit Minkowski coordinates. So I take Minkowski coordinates and now look at only linear transformations between them. Then all transformations are of that form. So they are Lorentz transformations. So in a way, the Lorentz transformations are just very particular coordinate transformations but it's special for two reasons. One is a physical reason, the flatness of space-time, which I need to make sure that this holds everywhere. Otherwise, it's only true at one point. And the additional non-physical reason that I just only consider coordinate systems that are linearly depending on each other. And actually, they are then both Minkowski coordinate systems. So that's essentially in what sense special relativity is special. So it's really in two different ways special. Okay, I think time is already, it's getting quite late. I think I overrun already a bit. So let us stop here. And maybe just as a very brief outlook, on Thursday, we will introduce, first of all, coordinates still in flat space-time, special coordinates called Rindler coordinates. And these coordinates will be particularly useful. They are actually not Minkowski coordinates, so they are curved coordinates. They are not nonlinear transformations. They will be particularly useful to study accelerated observers. And then, as a next step, we will study an observer who hovers above the horizon of a black hole. This has to be accelerated, otherwise he would fall into the black hole. So it turns out that these Rindler coordinates will be particularly useful to study the region outside of the horizon of a black hole from the viewpoint of an observer who just stays there. So that's essentially the reason why we will introduce Rindler coordinates, because our goal is to understand black holes. So that's what we start to do on Thursday.